Hello, everyone. I'm Dina Katabi. I'm professor in ECS. And today we're going to talk about systems that learn. And most of you are thinking about cloud systems, about servers, computers, all of the IoTs, all of that stuff. Not about some small device that we all have, which is our wireless devices, like your Wi-Fi router, for example, at home. So I want to talk about what AI can bring to simple wireless devices, and I'm going to use Wi-Fi box at home as an example to tell you about the power that we can bring to them with machine learning. So can a Wi-Fi box tell you whether someone has Parkinson's disease? What do you guys think? Okay, I see thumbs ups, so yes. Okay. I see, it's unfair advantage. I don't know whether this thing is moving stuff. Okay, here. Okay. So imagine if a box, not exactly your Wi-Fi box that you have at home, but a box that actually I do have literally at home, that sits in the background of the home, uses radio signal that bounces around that we are all swimming in, and just analyze those radio signals using machine learning to be able to tell our physiology, your motor symptoms, your sleep, not just when you are asleep, whether you are asleep or awake, whether you are dreaming, for example, during any particular time at sleep, your respiratory signal, even like for people who need help from caregivers, like whether they are getting that proper help. Can we do that by simply analyzing the radio signals? And indeed, we can. We call this box the Emerald box. It looks like a Wi-Fi box, but it has internally neural network systems that analyze these radio signals that bounce around to extract these physiological signals from vital signs to sleep to motor symptoms and others. So let me show you a few examples of this. So this is one of the offices that we have across the street in the CSAIL building. And you see here one of my students. The Wi-Fi, our device is not even in the same room. It's in the adjacent office. So we're going to monitor this guy through the wall where like this big arrow points, because we know that radio signals can traverse walls and occlusions. And this red dot here is where the device thinks this person is standing right now. Now, if I play this, and as he moves, you can see that the red dot is moving with him. So we can track his movement quite accurately, just purely because when he moves, he changes the electromagnetic waves around him. There are no sensors on him, no cell phone, wristbands, nothing. Purely passively. And as you can see, very accurately. Now, apart from motion, what can we else get? First, I want to emphasize that everything that we monitor, of course, we have peer-reviewed publications that shows that in comparison to the gold standard, we can get it very accurately. Okay? But we can also monitor, as I said, your sleep. When you go to sleep, your brain waves change, and you enter different stages: awake, light sleep, deep sleep, and REM, rapid eye movements. And these sleep stages are underlying many diseases, not just sleep disorders. For example, REM has many connections to depression and antidepressant, for example, change with REM changes when people take antidepressant. Deep sleep is also connected to Alzheimer, and the slow waves during deep sleep, impairment in those slow waves has been associated with Alzheimer's. So can we get sleep very accurately? Can we get sleep staging? Today, if you want to get sleep staging, you send someone to a sleep lab. They put these electrodes on his head and body, and they ask him to sleep like this. Yeah, he wasn't happy with this experiment. I don't know how many of you guys have been to a sleep lab, but it's a weird experience. And anyone who went through this, you're just like, is this how you monitor my sleep? Definitely, I didn't sleep naturally and normally, and it's not representative, but this is actually how we monitor sleep today. And not just that, of course, you can't have the person sleep every night in the sleep lab with these things on him. So let me show you how we monitor sleep. This is our wireless device, Emerald. We transmit very low power wireless signal analyzer reflections using machine learning, and it spits out something called a hypnogram. A hypnogram is what you get in a sleep lab. For every 30 seconds of sleep, it tells you whether you are in light sleep, deep sleep, REM, etc. So actually, this is exactly the hypnogram. And again, as I told you, everything that we do, we compare to the gold standard. In the case of sleep, it's that device called PSG, where you have all of these sensors on the person's head and body, and we show that we are very highly accurate. This guy is sitting like you guys, and what we are monitoring there, his breathing. We ask him to inhale, exhale. We ask him to hold his breath, and you can see the signal stays at a steady level because he exhaled, he did not inhale. Again, everything is compared to the gold standard in case of breathing. It's an FDA-approved chest band for monitoring breathing. Over the last 3-4 years, we took this technology and we started working with doctors, pharmaceutical companies, biotech, to actually use it with real patients. And as we are talking now, these devices sitting in the home of people who have Parkinson's, Alzheimer's, depression, atopic dermatitis, a variety of diseases, trying to understand the physiology and how the physiology changes with the disease and changes with the therapy. And I want to show you some of the results from that. Basically, once you have such powerful information about our physiology, what are the new things that you can do that seem to be infeasible at the surface in today's medicine? So now let's talk about Parkinson's disease. So I'm sure all of you guys have heard of Parkinson's disease, but perhaps you don't know that Parkinson's disease is the fastest growing neurological disease in the world. It is the second most common neurological disease after Alzheimer's, but it's the fastest growing neurological disease. Of course, Parkinson, we know it from the tremor and the stiffness of the motion. We all remember Michael J. Fox, who has a big foundation, who got Parkinson very early on, the actor, the famous actor. So the problem, one of the problems, of course, there are many problems with Parkinson, but one of the key problems with Parkinson is like Alzheimer, the disease is diagnosed very late. So the disease happens, and then we take about 10 years to diagnose the disease. And one of the reasons is because we diagnose the disease from the motor symptoms. We don't know that someone has Parkinson until we start seeing that they are tremoring, they are having stiffness of motion, and start complaining about that. But that happens later in the disease. But by the time the motor symptoms appear in the disease, about 40 to 80% of the neurons, the dopaminergic neurons, already impaired and damaged. So imagine if we actually diagnose a disease when 80% of the important neurons for that particular disease already damaged. Like how many chances we have with such a disease. So here what we want to do, we want to ask, can we diagnose the disease early by using the information, the physiology that we see using these wireless devices in the patient's home, in people who have Parkinson versus people who don't have Parkinson's. So we ask a very simple question. Can AI detect Parkinson's disease from breathing? Because breathing, there are some insights that breathing can happen before actually the motor symptoms. So what we did, we took respiratory signal. I showed you that we can get breathing very easily from our wireless device. We trained a neural network to answer 2 questions. Does this person have Parkinson's? And if they do have Parkinson's, what is the severity of their disease according to the gold standard? And this is a very big study that we use both the wireless data that we have, and also we work and pull data from Mayo Clinic, from University of Rochester, from MGH, and let me show you the result. So what do you think? Of course, we can do it. And here is what's called the ROC curve. These are very commonly used in medicine and also in machine learning. So on one axis, you see the sensitivity of the classifier. On another axis, you see actually 1 minus the specificity of the classifier. If you haven't seen this curve, all that you care about is the area under the curve, what's called AUC, and you can interpret this as accuracy. So we can, with an accuracy that is about 90%, tell whether this breathing signal comes from somebody who has Parkinson's or doesn't. So this is very surprising because even if you ask the best neuroscientists and the Parkinson expert, can you look at their breathing and tell whether they have Parkinson's or not? He would just tell you, no way. In fact, my collaborators, my clinical collaborators told me that, okay, yeah, we know that the breathing changes in Parkinson, but there is no way to detect it from the breathing. But the machine can, because it looks at different things that we as humans, we don't think the same way. We don't focus on the same feature that a machine learning algorithm can focus on. Now, of course, the next, so can I finish? And I'll take some questions. Okay, so of course, can it detect Parkinson earlier before the disease actually is detected by a doctor, is clinically diagnosed? Now, of course, this is a harder question because it means that you have to somehow monitor people that you know downstream that are going to have Parkinson's. So we don't have those people, but we have small study where we have respiratory signal from 2 visits to the doctor, and those 2 visits are separated by 6 years. And there are some people who on the first visit they came and said, I don't have Parkinson, but later, 6 years later, when they came for the second visit, they said, I was diagnosed with Parkinson. So it's a small data set, but it gives us an initial understanding whether the machine learning can do it or not. And I want you to look at this graph. The blue ones are the people who eventually, 6 years later when they came, they said, I was diagnosed with Parkinson's. And the red ones, there are the people who 6 years later came and said, nobody diagnosed me with Parkinson throughout this time. And you can see that the machine learning algorithm already, much earlier, knew that those people, there's something wrong. At least for 75% of those people, there was something wrong that the machine learning was able to point out and say, I think those people do have Parkinson's already. So this is very promising as an early way of detecting Parkinson's. I want to end with talking about generative models. So we all talk about generative AI nowadays, but the way we think about generative AI is that like something like ChatGPT. I give you text, you generate more text with a lot of semantics, or I give you text and you generate an image. So for example, today, you can like give DALL-E 2 something like saying a corgi playing a flame-throwing trumpet, and we'll generate a picture like this for you. Now the question that we ask, can we give radio signals to generative models, and they will generate a clinically complex signal like EEG, like your full picture of your EEG signals from your brain. And this is very, very recent results, and we are looking at these generative models that can synthesize generative clinical data that is meaningful, that can preserve the disease that the person has. And let me show you just very peek at those results. So this is somebody who has Alzheimer's, and here is his spectrogram of his EEG signal throughout the night. And this is something that was generated from our neural network about his EEG signal from the radio signal. So you can see that it's pretty much matching. It understands where the signal should go to different bands, generating something that looks like the EEG of this person. So with this, basically, our system that can learn actually probably to do things that we and even our expert doctors cannot do, basically take a peek inside the brain and with AI and radio signal to try to understand difficult diseases such as Parkinson's, Alzheimer's, depression, etc. Thank you very much.